speed. Like, this is just so much faster to do. And that's true to this day. Yeah.
Why couldn't you just say, okay, well, I'm going to add 2 more variables to this one that's cosine of theta, one that's sine of theta, so that you don't have to recalculate that?
You do. So what you do, you wouldn't calculate, you absolutely only would calculate the cosine once.
Yeah.
And you only calculate the sine once.
Well, then what makes that one so much better than that one? Because that one you have to calculate E1 and E2.
But you don't. See, that's the that's actually part of the game. So when you're doing numerical integration, right, at t equals 0, yes, you will. Okay, so at t equals 0, you do this calculation once. But then what you're going to do is integrate these parameters directly. So you have, at each value of time, you don't even have theta anymore. You just have E0 at time t plus delta t. So at each value of time, you have these, because that's what you're integrating, and then you very, very quickly calculating this. Where over here, you again, if you say, I'm going to start in the lambda world, and you start in the lambda world, great, you do this calculation. And then you say, now give me the next value of lambda 1, 2, 3. You still have to calculate the cosine. You're right, though. You'd only calculate the sine and cosine once. And by the way, supposedly, so no one really cares about us anymore in the computation. No one out there in Intel and AMD care that much about us. But there's hope that people still care about computation. So if you notice that the sine and cosine share the same, almost the same exact functions. Actually, that was theta. So that's 1 minus theta squared over 2 factorial plus theta to the 4th over 4 factorial. If you start looking at these, you realize that there's a lot of tricks you play when you calculate sine. Like, for example, you don't actually calculate theta to the 5th. What you do is you take your calculation of theta to the cubed and you multiply by theta squared, and you pre-calculate theta squared, because guess what? When you get to the theta to the 7th, you're just going to take your pre-calculation of theta squared and multiply it by theta to the 5th. So the game is you actually just you have this pre-calculated theta squared, okay, and then you just keep on multiplying it as you go. All right, so this is how you do the computation. And people who do the sine and cosine, they work so hard at getting squishing. And what you realize is, well, if you're going to have to calculate both sine and cosine, and they're not that different, here's a 3 factorial, 2 factorial, 5, you see that, wow, I can speed up my calculation of sine and cosine if I knew I have to calculate them both anyways. So there's a hope that there will be part of the C++ and future language, there will be a sine cosine calculator. So right now you can calculate the sine function, you can calculate the cosine function, but you actually have to take 2 different calls to make it happen. So we'd have like a sine cosine function, it would return one or the other, and then as a return function, and return the second as an argument. So there's hope that even this would be speeded up, but even if it gets speeded up, it would be reduced probably from, instead of 50 plus 50 is 100, we're down to probably 70. All right? It's still got major overhead. But we do sine and cosine calculations all the time. In our game in dynamics, it's just incessant all the time, all the time, all the time, all the time. So there's hope in computation land that maybe the C++ and C people will care enough about us, because JavaScript probably don't. I mean, that's more web and Facebook, where sine and cosines don't play a major role. But these, regardless, are going to be so much faster. Now, once you get the game of, hey, lambda 1 squared plus lambda 2 squared plus lambda 3 squared equals 1, when you come over here, just by squaring these, you say, if I take this, 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 and this, and square them, you'll have cosine theta over 2 squared plus this squared, this squared, this squared. This is the same as lambda 1 squared plus lambda 2 squared plus lambda 3 squared times the sine of theta over 2 squared plus cosine theta over 2 squared. You already knew that was 1, so it turns out this is cosine squared plus sine squared is 1. So that's how these parameters end up with that constraint. It's by their definition that this squared plus this squared plus this squared plus this squared, that all, when you square them out, equals 1. Okay, and it comes directly from their definition, and just an idea that sine squared plus cosine squared equals 1, and there's a constraint on these as well. All right, so that's where the constraint comes from. It's, again, purely from the definition, and this is not a generic quaternion. This is a very specific version of the parameters, which are a specific version of quaternions in general. All right, so these are the parameters, and now the last thing we're going to do is just go back to, all right, we've now talked about rotations in terms of simple angle axis, and we've talked about rotations in terms of just half-angle formulas. That's all that happened. So to go from here to here is purely just half-angle formulas. Nothing fancy. Nothing like, oh, mind-bending. Now, I wouldn't have not, I don't know if you guys remember, does anybody remember what a half-angle formula looks like?
Yeah.
All right, so someone on this side of the table, you remember like cosine something, how it relates to minus cosine over 2 or something like that. Cosine 2x. Let's do, how about a double angle formula? Cosine 2x. How about this? I know. Let's do this. How about cosine of a plus b? How about we start there? Anybody remember that one? On this side of the table. Okay, cosine a, cos b. All right, and then if you say, now we'll do cosine of x plus x, otherwise known as cosine 2x, and that's going to be okay, good. And then, so that's the same as cosine 2x, right? And then you can then take like your sine squared and replace it with, yeah, good. So you can replace this as, this is the same as 1 minus cosine squared. All right, so that becomes 2 cosine squared x minus 1. All right, and then, so then you divide by 2's, and you can do like cosine of x equals 2 cos squared x of 2 minus 1. Is that right? Yeah. All right, so this is sort of like the birthplace of how it goes from here to here. It's these kind of half angle and double angle formulas. All right, so I just want to make sure it's not like super mysterious. It's just a super clever way of avoiding a sine and cosine. So that in itself, I thought was pretty brilliant insights on him. But the real kicker happened here was the axis angle stuff also given desired orientation, find 1, 2, 3 theta to okay, so given that you say I have the aircraft or the machine set, like, look, I know that it used to be here, I want it to be there, find these. And the answer is, yeah, you can try to do it straightforward, and the algorithm for doing this is, let's see if there's a, okay. So the first problem that we talked about was, given a laptop and given that there's a vector and given that there's an angle, find the rotation table, okay? So that's this part, not so hard. The other part is now, given that I know exactly where I want to be, what were the lambdas to get you there? The answer to that question is actually done by instead leave this, say, that's nice, come over and work in Math World. And you work in Math World, and the algorithm is in section 8.6.3. And sometimes this is called, inverse kinematics. And this is actually sort of hard. All right. But your job is not to necessarily memorize or anything, but to realize it's like all these algorithms have been worked out. And so this algorithm 863, I was first privy to it in '93, and then I made some modifications to it. So there's a little black section in it that just sort of says if you want to be slightly more efficient with computation, just use the stuff inside the black line. So here's the old stuff. There's a paper by, I think it was Shepard, let's see, I forget who it was who wrote this paper. But this is the aerospace business was like, okay, look, I want to take a spacecraft, I want to dock two spacecraft together. So I know exactly what my desired orientation on my spacecraft is. So I know my desired orientation. How do I actually reorient my aircraft? So how do I get there? How do I do these? And the answer actually is to actually start over here and think here. So go here, calculate these, and then calculate the thetas and the lambdas. So you do the calculations of these because the algorithm for doing the math is much more robust. It turns out that the math, so math for the lambda 1, lambda 2, lambda 3, and theta has two major problems. One, problems, I'll just put problems with the math. And it's not problems with the physics. The physics is so much easier to think about lambda theta. But the problems with the math are A, computational cost. And B, they're loaded with singularities. Okay? There's no problem with the physics. The problem with the physics is that these have no physical meaning, none. It does not, take some angle divided by 2, take its cosine. What does it mean? It means nothing. It means you get to dinner early. That's what it meant for the kids of Euler. For you, it means it's a really clever trick. So if you say, I really want to know how to do a reorientation, I know my desired orientation, how do I get there? You look it up. It's literally like, don't memorize, don't look it up. The proof is in the book. The proof is really carefully done. But even the proof for this is, it's almost 2 full pages. And all it involves is a bunch of tricks. And every trick you'll see is like, it's squaring, it's a trig formula, it's whatever, but it's nothing hard. It's not like, oh, it's super complicated. It's super simple, but how would you have known to put that steps together? I don't know. It's magic, like to put all those steps in that sequence to actually give you the algorithm. But anyways, that's how you actually get the algorithm. All right, so quaternions are used to do inverse kinematics to actually figure out how do you find, given your orientation, how do I actually do the flipping maneuvers. All right, so that's there. The last thing, and then we'll stop, and then I'll send out a few exercises so you can sort of see how to program, and I'll post on motiongenesis.com. I'll post the answers to the exercises so you don't have to feel like you're struggling. And I'm happy to come in and we can have if you're working on it and you still haven't got the answers, I'll come in and we'll just sit together and work on them together because that's the easiest way to do this. The other thing that you should probably see, and it's one of the things I worked so hard on, and I was so frustrated with the fact I couldn't find it anywhere, even in Kane's books, were the following. I hopefully beat into you that omega is not theta dot k. So that in general, I've told you over again, it's not theta dot k, theta dot lambda, or whatever. Okay. So what's weird is a lot of people will say, yes, omega is theta dot lambda, including Wikipedia. We went on there and found love. It's not theta dot lambda, and I sort of said, no, it's not, no, it's not. And people quote Euler all the time, but Euler said, and he did. He said, you can always reorient an object by go around one axis by one angle. And he did, he said that. What he didn't say was, therefore, you can then just differentiate just the angle without considering what happens to the axis to figure out what omega is. This is true, so this is true if and only if lambda remains unchanged in both A and B. And unchanged means, fixed, doesn't change direction. So either theta can change, or lambda can change, or both can change. So in 2D world, yeah, lambda never changes. Lambda stays always fixed in A and B, and this is simple 2D stuff. So in 2D, life is good. So I'm going to put under the equal sign, this is 2D, life is good, and this is how this simple angle axis stuff works in 2D. Just always revolve around the same axis, don't change your axis, and make sure this axis doesn't change in B and A. All right, so the visual on that is if you take this ball, you can say, I'm going to rotate by an angle theta. Okay, so you rotate, and you can continue to rotate by theta, and as long as this vector here doesn't change, so that's never going to change in the ball, because it's actually painted into the ball. But as long as it doesn't change its orientation of the room. Now, it can do this, but it's a unit vector. If someone says, does this unit vector change in the rim? The answer is no. It has the same magnitude, 1, and it has the same direction in the room. So it's, you can translate to your free consent, but so you do this, this says, yes, this actually works. However, if you take this ball and then you do something like that, right, now this vector is no longer staying in the same orientation in the room. So what happens now? Well, this I actually struggled long and hard on, and you go to chapter 9 next. So this is where the chapter 9 stuff comes in. All right, so what is the relationship between omega and theta dot and lambda? And the answer is this. It's, again, hard to find this anywhere. Theta dot lambda, so this is the first starting point. So it starts right, but then you have a plus sign, and the next thing you do is it's the sine of theta times the change in lambda with respect to time. And you can do this in either A or B, so in both of them are there. I'll just write out the one in terms of B. The one in terms of A looks exactly the same, except there's an A here. Plus, and then cosine theta minus 1 times lambda cross d lambda dt. All right, so here's the game. If d lambda dt in B is 0, then these two terms go away and you get like your simple 2D stuff. So this is your answer. What's sort of nice to know is, hey, wait a minute, I'm seeing these 1 minus cosine thetas again. Well, that's interesting. Those are exactly like what happened with the other parameters. I saw these sines of thetas and 1 minus cosine thetas. Wow, that's sort of weird. Now, the problems with math for the lambda 1, lambda 2, lambda 3, and theta actually keep on getting worse. So if now someone says, given omega, b, and a, find theta dot and then d lambda dt. Okay? So now we're doing, again, an inverse problem. So given this, find those. And it turns out it's not that bad, because if you look at it, lambda and lambda dt are actually orthogonal. So this, and this form actually a orthogonal basis, like a good old, IJK type of basis. So you can solve, and when you solve it, and this all this is on the book, it's just theta dot is omega b and a dot lambda. So that's not so bad. And then the other one, though, not so good. And this is d lambda dt in B equals 1/2, and I'm going to write this down because this is actually the linchpin to like why we do what we do. Cosine theta over 2 divided by sine of theta over 2 times omega b and a minus theta dot lambda plus lambda cross omega b and a. All right, so this is equation 3 in chapter 9. So this is equation 9.3. This one is fine. This one has a major problem. Divide by 0 when theta equals 0 degrees. All right, so right off the bat, you're like, this isn't going to work for you. All right, so now you're on the spot. Someone says, you have a divide by zero problem. How do you get rid of divide by zero problems? Say it nice and loud, you're right on it.
Multiply by sine of
Sine of
theta
who?
over 2.
Sine of theta over 2. So, wow, isn't that clever? Multiply by sine theta over 2. I wonder who thought of that first. Oh, it was Euler. So, Euler just goes, wait a minute, if I just multiply this left-hand side by sine theta over 2, and just last night, I just invented these Euler parameters, which are sine theta over 2 times, guess what, lambda. Then all of a sudden, you get rid of your divide by zero here, and now you're into, oh, I actually now have a 4-parameter set that actually doesn't have a divide by zero error. So all that happens next is you say, multiply by sine theta over 2. When I do that, you end up with cosine theta over 2. So these are all, again, these half-angle formulas show up. And now it's like just a really clever trick to get rid of the singularity. And that's it. So quaternions are pure math. Our version of quaternion are really the Euler parameter version of it. And what I'll send out is like an assignment. You can do it as you wish, but the assignment comes down to doing inverse kinematics